This is the second part of entropy chapter actually. So we will be going into 7.1, yeah? And the objective would be to apply the second law of thermodynamics to processes, define a new properties called entropy to quantify the second law effects, establish the increase of entropy principles, and so on. You can just read all the objective of the chapters here. Okay. As what we have studied from before, yeah, an irreversible heat engine, for example, is less efficient than a reversible one, because reversible one, I've told you, is the perfect one, yeah. Okay, so another important inequality that has been major consequence in thermodynamics is the Clausius inequality. Yeah, this is the Clausius inequality to prove the statement of Clausius inequality. Now there are new symbols here. Can you see the symbols here with a cycle, with the integration sign? Okay, the symbols with a circle in the middle here is used to indicate that the integration is performed over the entire cycle. Now what is a cycle? Remember what I told you, start from the initial, go to the second and come back to the initial. This is a complete cycle. Yeah. So any heat transfer to or from a system can be considered to consist a differential amount of heat transfer. Yeah. Then the cyclic integral can be viewed as a sum of the differential amount of the heat transfer divided by the temperature at the boundary. Okay. Now this whole diagram here demonstrates the validity of Clausius inequality. So first, you consider a system connected to the thermal energy reservoir at a constant thermodynamics, yeah, here. Okay, and then through a reversible cyclic device. So the cyclic device received a QR, a sigma QR from the reservoir, and supplies it heat to the whole system down here. Okay, whose temperature at the part of the boundary is T. While producing the work, W reversible. Okay, the system produces work system as well. Okay, so as a result of the heat transfer, applying the energy balance and combining them, yeah, you will get all these equations here. So this whole thing is actually to prove, yeah, to prove that the equality in Clausius inequality holds for totally and just internally reversible cycles, and the inequality for the irreversibles one. So your scope is not to prove the formula but to use them only, so don't have to worry much about proving the formula. Okay, so this is where it's heading to. Yeah, can you see this graph here? So this is an irreversible process and this is a reversible process. So the change between the reversible and the irreversible, you minus, that would be the how much is the friction, correct or not? Or how much is the irreversibilities, which is actually associated with entropy, because entropy is disorderness. So do you understand or not? Yeah? Okay, that's what we are looking at. So in special cases for isothermal heat transfer processes, so this would be the valid formula to calculate the entropy. Yeah. Now remember, entropy is an extensive property and you can actually look up for the entropy from the steam table itself. Yeah. It's a slightly different from enthalpy. So now let's consider a cycle that is made up of two processes. Process 1 to 2, which is reversible or irreversible, and process 2 to 1, which is internally reversible, which is shown in this figure. Yeah. Okay. So this is actually from the Clausius inequality. So from this diagram here, it can be proven that the inequality holds for an internal reversible process and the inequality for an irreversible process. Yeah. So the inequality sign preceding the relationship of the constant reminder that the entropy change for the closed system during an irreversible process is always greater than the entropy transfer itself. Okay, so entropy generated or created during a irreversible process. Yeah, so I repeat, entropy is generated or created during the irreversible process. Yeah, now remember, energy cannot be created nor generated, but entropy can. Yeah, And entropy, which is entropy generated, which is Sgen will always be a positive or a zero value. Yeah, it cannot be a negative. Yeah. Okay. Now, if it's zero value, then the system is perfect. Yeah, it's a reversible process. But if the value is positive, then there is certain amount of disorderness in the system itself. So that's what it means. Yeah. Okay. Okay. So if you see here, can you see this line here? It will be greater than 0, and this one, if equal, it's a reversible process, it's a perfect process, and if it's 0 here, it means this is actually an impossible process. Yeah. Okay. So the equation before this. Okay, let's look at this equation here. Delta S isolated is greater than 0. So this equation can be expressed as entropy of an isolated system during a process always increase, or in a limiting case of a reversible process remains constant. Yeah, it increase or remains constant. In other words, it never decrease. Like what I've explained to you, it cannot become negative. This is known as the increase of entropy principle. Yeah, note that the absence of a heat transfer, entropy change is due to irreversibilities only. The effect is always in to increase the entropy. So entropy is actually an extensive property. So thus total entropy of a system is equal to the sum of entropies part of the system. Okay, let's look at an isolated system which may consist of many subsystems here. Yeah, many subsystems here. Okay, a system and its surrounding, for example, constitute of an isolated system since both there is no heat, work and mass transfer. Therefore, system and its surrounding can be viewed by two subsystems of an isolated system, and the entropy change of the isolated system during a process is the sum of entropy change of the system and its surrounding, which is equal to the entropy generation since an isolated system involves no entropy transfer. Okay, so that is the explanation for this part here. Okay, there are some concluding remarks about entropy itself. Let's go through the remarks here. Process can occur in only certain direction, not in any direction. A process must proceed in the direction that complies with the increase of entropy principle. It's because you cannot have negative Sgen, right? Yeah. So entropy is a non-conserved property because it can be created. Yeah, remember what I told you? And there's no such thing as conservation of entropy principle. Energy, yes, but not entropy. Entropy is conserved during the idealized reversible processes only. So increase during all actual process. So the performance of an engineering system is actually degraded by the presence of irreversibility. So this is the reason why we are actually studying this topic, because we need to calculate how much entropy that can be generated, because that shows the performance of the engineering device itself. Yeah. So with this, actually let's move on to an example that I picked from the textbook. Let's discuss this example. So this is the question. A heat source is at 800 Kelvin. So the heat source for both, the heat source for both is actually 800 Kelvin. Okay, heat losses is 2000 kilojoule for both. So one is going to the sink of 500 and the other is actually to the sink of 750 Kelvin. So what you need to do is determine which heat transfer is more irreversible. Yeah, that is the question. Okay, you have to determine which is more irreversible. Okay, let's calculate for heat transfer A, situation A, which is to 500. So source, delta S of source is Q source divided by temperature source, which is in this case negative 2000 divided by 800. So it's negative 2.5, and the sink would be 2000 positive because it's receiving. Yeah, this is actually giving away. That's the reason why the source is negative. and is receiving 500. So we have positive 4.0. Remember, just look at this. Positive and negative sign plays an important role in this. Yeah. So what is the SGen here? That would be the total, which is the source plus the sink. So for case A, it is 1.5 kilojoule. It means to the source, to the sink of 500 Kelvin, the SGen is 1.5. Now let's look at the second part of the calculation, which is part B, which is repeated but to 750. Okay, for 750 you repeat the same thing, but the value is 0.2 compared to 1.5. So what is the concluding statement? The total entropy change for the part B is smaller, and therefore it is less irreversible. This is expected since the process B involves a smaller temperature difference, thus a smaller irreversibility. So this is the concluding calculation for this chapter. So with this, I've ended chapter 7.1 and 7.2. That's all for this video. Thank you.